All right, let's dive in. Today, we're tackling a problem that is, and I mean this literally, at the core of our digital lives, finding the shortest path. We're going to break down 3 absolute legends of the algorithm world. The goal? To make you an expert, ready for any exam question that comes your way. So, let's open up the toolkit and see what we've got.
You know, it all boils down to this one simple question. Whether you're trying to get across town using your phone's GPS or you're sending an email across the internet, the goal is always to find the most efficient route. And efficient doesn't just mean distance. It could be time, it could be money, it could be any cost we want to keep as low as possible. And that's the fundamental problem these amazing algorithms were designed to solve.
So, here's the plan for today. Think of this as getting to know 3 essential tools in your computer science toolkit. First, we'll really nail down the core problem. Then, we'll look at each tool, one by one. We've got Bellman-Ford, we've got Dijkstra's, and we've got Floyd-Warshall. And finally, the best part, we'll put them all head-to-head in a big face-off, so you'll know exactly which tool to grab when you need it.
Okay, so let's get right to the heart of it. If you have a simple graph where every path is equal, finding the shortest route is pretty easy. You just count the number of stops, right? An algorithm like breadth first search can handle that, no problem. But come on, the real world is way more complicated. Roads have different speed limits, network cables have different speeds. That's where weighted graphs come in, and that's when you need to bring out the big guns.
And that brings us to the official definition. The shortest path problem isn't about finding the route with the fewest turns. No, it's about finding the path where the sum of all the weights along the way is the absolute minimum. It's the classic difference between the shortest route and the quickest route. You might take a few more turns, but if you're on highways instead of city streets, you'll get there faster. That's what we're trying to find.
All right, tool number 1. Let's talk about the Bellman-Ford algorithm. I like to call this one the safe bet. Why? Because it's super robust, it's incredibly reliable, and it can handle some really tricky situations that would totally break other algorithms.
Bellman-Ford has a few key features. It finds the shortest path from one starting point to all others. But its real superpower, the thing that makes it so special, is that it can handle negative edge weights. Now what's that? Well, think of a negative weight as a reward or a shortcut, or maybe a discount for taking a certain path. Bellman-Ford can also spot something really dangerous called a negative cycle. That's a loop that you could travel forever, getting a better and better score, which makes finding a shortest path totally meaningless.
So how on earth does it work? Well, the idea is actually pretty straightforward. First, you set up your starting conditions. The distance to your starting node is 0, because, well, you're already there. The distance to every other node, we set that to infinity. Now that's just a fancy way of saying, at this moment, we have no idea how to get there, so we'll just assume it's unreachable.
The algorithm then works in rounds. And in every single round, it goes through every single edge in the entire graph. For each edge, it does something called relaxation. All that means is it asks a simple question. Hey, if I take this path, does it give me a shorter route to the destination than the one I already know about? If the answer is yes, great. We update our map with the new shorter distance.
And it just keeps doing this over and over, round after round, checking every edge and updating the distances whenever it finds a better way. And here's the magic. At some point, the algorithm will do a full round, check every single edge, and realize that nothing can be improved. No paths got shorter. At that exact moment, it knows it's done. It has found the best possible paths.
Okay, exam time. You have to know the complexity. For Bellman-Ford, it's O(n)(m). So why is that? Well, it's because it runs for n-1 rounds in the worst case, and in each of those rounds, it has to look at all m edges. This makes it super thorough, which is great, but it also means it can be pretty slow if your graph has a ton of connections. That's the trade-off you make for all that power and safety.
Okay, on to our next tool. If Bellman-Ford is the safe and steady option, Dijkstra's algorithm is the speed demon. It's the fast lane. When you absolutely need speed and you know your graph plays by the rules, this is the one you reach for.
And this slide right here shows you the biggest trade-off in this whole topic. Dijkstra's is way, way faster. But it comes with one enormous, non-negotiable rule. Your graph absolutely cannot have any negative edge weights. Not a single one. If it does, the algorithm won't just be slow, it will give you the wrong answer.
So what's its secret? How is it so fast? Well, Dijkstra's is a greedy algorithm. It doesn't worry about the whole map, it just makes the best possible local choice at every single step. It keeps a sorted list of places to visit, called a priority queue,
and it always just grabs the closest unprocessed node off the top of that list, declares its path final, updates its neighbors, and then it moves on and never looks back.
In this right here, this is the key insight. This is so important. Unlike Bellman Forward, which might go back and revise a path's cost, once Dijkstra's picks a node to process, that's it. Lock it in. The shortest path to that node has been found, period. It never second-guesses itself, and that's what makes it so incredibly efficient.
But here's the catch. This is the classic exam trap. Because it's so greedy, Dijkstra's can be fooled. Imagine there are two ways to get somewhere. Path A looks really cheap at the start. Path B looks really expensive. Dijkstra's will greedily jump on Path A. What it can't see is that way down Path B, there's a massive negative edge, a huge shortcut that would have made it the better choice overall. But it's too late. Dijkstra's already committed, it won't look back, and so it gets the wrong answer.
So what's the reward for this risky, greedy behavior? A fantastic time complexity, O of n plus m log m. That log m is a huge improvement over Bellman Ford's n. It makes Dijkstra as the undisputed champion for big graphs, as long as you can make that one crucial guarantee: no negative edges.
All right, it's time for our third and final tool. And for this one, we have to completely change how we're thinking. Bellman Ford and Dijkstra's, they're about finding the best path from a single starting point. Floyd Warshaw, though, this is the grand planner. This is for when you want to create a complete road atlas of every possible journey. That's right. Floyd Warshaw solves what's called the all-pair shortest path problem. You run this thing just once, and what you get back is a complete table of the shortest distance from any node you can imagine to any other node. It's not about just one trip, it's about all of them, all at once. The way it works is just elegant. For every possible pair of nodes, let's call them I and J, it then considers every single other node, we'll call that one K, as a potential middleman. And it just asks, over and over, is the path from I to J shorter if we stop at K along the way? It checks this for every possible combination of I, J, and K, and slowly, piece by piece, it builds a perfect map where every single path is the absolute shortest it can be. Now, all this power comes at a pretty steep price, a time complexity of O of n cubed. Oof, yeah, that's n cubed. You can almost see the 3 nested loops in the code just by looking at that. This means it's really only practical for smaller graphs, but its big advantage, it's often incredibly simple to write the code for it. Okay, team, we filled our toolkit. Now for the most important part, especially if you've got an exam coming up, the face-off. We're going to put everything together so you know without a doubt which algorithm to pick for any problem they throw at you.
This is the slide to screenshot. This is your cheat sheet. Let's break it down. If the problem is about finding paths from one starting point and you might have negative edges, you have to use Bellman Ford. If it's a single source problem and you can promise there are no negative edges, go with Dijkstra's. It's way faster. And if the question asks for the shortest path between all pairs of nodes, that's what Floyd Warshaw was born to do.
So, when you're studying, here's what to focus on. 1. Know the rules cold, especially that negative edge rule for Dijkstra's. 2. Understand the trade-offs. It's almost always a question of speed versus safety and features. 3. Practice tracing them on paper. I guarantee you'll be asked to walk through an example. And 4. Memorize those time complexities. They're your guide to knowing which tool is even possible to use for a given size of graph.
And let's just end on this one thought. These algorithms, they were invented back in the 1950s, and yet they are still the fundamental building blocks of the technology we use every single day. That's just incredible. It makes you wonder, right? As our world gets even more complex, with real-time traffic, dynamic network costs, and all sorts of new constraints, what kind of even smarter pathfinding algorithms will we need to invent next? That's the challenge for the future. Thanks for tuning in, and I hope this was helpful.